welcome. This video I'm going to introduce the subject of electric potential, something that's related to electric field. But the name may sound a little unusual, electric potential, but it's also called voltage, which is probably one of the most familiar terms in electricity to people. Electric potential and electric field. What is the potential and how is it related to the field? I want to begin by telling you that there are two ways to solve problems. In this context, we're talking about electrical problems, but this also shows up in other areas as well in physics. There's a vector method and a scalar method. Scalar is just another word for number. So the vector method and the scalar method. The vector method is what we've been doing so far in the course. We started with the electric force, introduced the concept of the electric field, and then developed this concept by saying that one charge can produce an electric field, and it exerts a force on another charge through this relation right here, Q times. Q would be the second charge, and the electric field comes from the first charge, and that's the force that one charge has on another. So maybe you've enjoyed seeing those videos and seeing how to solve problems with vectors and the magnitude and the components and the angle and so forth. But maybe you're also thinking, is there a simpler way to do it, just using numbers? Well, here's the scalar method. Instead of force, we have potential energy. That seems like a very different concept. But I hope to show you they are related. What takes the place of the electric field? This capital V, which we can call either voltage or potential or electric potential. Then how are these two related? Well, the potential energy is Q times V. Suppose that one charge has the potential V. You bring a second charge Q nearby. The potential energy is Q times V. Okay. Develop these in more detail as we go along. But at this point, I just want to give you the overview. There's a vector method. There's a scalar method. The way these are related, force is related to change in potential energy. Field is related to change in potential or change in voltage. So that's how they are related, and let's begin the details. Start with the vector method, and also with a concept that you should have covered in Physics 1, work. Now here we have an electric field. I have it pointing down, I have a positive charge. We don't know how much work the field will do on the charge. Well, you should remember from Physics 1, work is force times displacement. And well, here have the arrow. The field is going to make a positive charge move down. The work, we say force times displacement. The key thing you have to keep track of in calculating work. To do work, there must be a displacement. The object has to move. And the force that moves it must be in the direction of the motion. So this downward direction I'm going to call Y, Y direction. So the work, W, is the force in the Y direction, F subscript Y, times the displacement, delta Y. Now, the force in the y direction will be equal to the charge Q times the field component in the y direction, E sub y. And the displacement delta y. So here is the work. The Fy delta y, or that's also equal to Q E sub y delta y, where Q refers to that charge. You may also remember Physics 1, something called the work-energy theorem. Work is equal to the change in kinetic energy. This is an important concept. When positive work is done, you increase the kinetic energy of the object, and so delta Ke is positive. There's also the concept of negative work. How can you have negative work? Negative work means you are removing kinetic energy, decreasing the kinetic energy. You're making something slow down. You get in a car, you step on the gas pedal, the car accelerates, the engine is doing positive work, increasing the velocity, increasing the kinetic energy of the car. You step on the brake pedal, car slows down. The car loses kinetic energy. So the brakes are doing negative work. Okay, quick review of work energy theorem. And work is a key concept here because it's going to allow us to relate the vector picture to the scalar picture. This shows you the vector picture. Force, field, displacement are vectors. What's the scalar picture? We're going to go back to what you should have had in Physics 1, conservation of energy. The electric field conserves energy. So here's our charge, and we have two levels, PE1, PE2, two different values of potential energy. Now, PE1 is larger than PE2. What does that mean? Means if there are no constraints on the system, that charge is going down. You don't need to talk about force. You can, you don't have to. You can say objects have a tendency to go to a state of lower potential energy. That's what's going to happen. Now, you can say, well, it's going because of the force. But you can turn it around. You can say, why is there a force? There's a force because there are different levels of potential energy. Okay. We won't worry about, what we use our starting point. We're just saying we can describe the same problem either by saying the object goes to lower potential energy or a force acts on the object. Now, the change in kinetic energy, delta Ke, is minus delta Pe. Why the negative sign? Because the potential energy is decreasing. Delta Pe is negative. The kinetic energy is increasing. So delta Ke is minus delta Pe. There's no friction, there's nothing, no energy lost. With these charges, we just have kinetic energy, potential energy. Ball rolls down a hill. Delta Pe is negative, goes faster. Delta Ke is positive. You throw a ball up in the air. As the ball rises, gains potential energy. Delta P is positive. Delta Ke is negative, slows down. Previously in the vector picture, the work equal to Q E sub y delta y. Now I can use the work to equate the two formulas. Q E sub y delta y equals minus delta Pe. That's the tie point. Now we define potential. Potential or voltage is capital V is the potential energy per charge. For a given charge, if you take that potential energy of the charge, divide it by the charge value, you get the potential. Now, therefore, since charge is a constant, any change in potential energy must be due to a change in potential. Delta PE, or just rearrange the equation, is Q times delta V. Previously, we stated this equation. So now I can substitute in this equation for delta PE. Q E sub y delta y is equal to Q minus Q delta V. We can strike Q out of the left, out of the right, divide both sides by delta y. Here we have kind of the thing we're looking for. Here is the relationship between electric field and potential, or electric field and voltage. The y component, electric field, is minus delta V over delta y. In other words, there is a component of the electric field in the y direction because the voltage changes in the y direction. Negative sign means that field points in the downward direction, points in the direction of decreasing potential. Now, this derivation was done assuming the charge moved in the y direction. You could equally well do the same derivation and call it x or y or z. So in 3 dimensions, the components of the electric field depend upon how does the voltage change in each direction. There's a field in the x direction if the voltage changes in the x direction. Field on the y, z, if voltage changes in those directions. Again, don't forget the negative sign. Negative sign means the field points in the downward direction. It points in the direction voltage decreases. There's an electric field where voltage changes. Where does voltage change? Look, picture of a typical 9-volt battery. You have a positive terminal and a negative terminal, or a higher potential, lower potential. A little bit hard to see, but if you look at the battery on the top, on the right-hand side, that is the negative terminal. Is there an electric field? Yes. There is an electric field pointing from the high potential to the low potential. We say from the plus to the minus. The lower battery lying on its side, you can see there is the positive of the higher potential terminal. On the right, electric field points from the higher to the lower. There's an electric field. What's happening? Nothing is happening because nothing's connected to the battery. But if you put a wire on that, between those two terminals, that field will cause charge to move from one to the other. Let's remember a topic covered in a previous lecture, conductor at equilibrium. We said at equilibrium, force, net force on charge is going to be 0. Since force is equal to Q times Z, if there is a charge and the force is 0, it must be the field is 0 at equilibrium. Therefore, if the electric field in each direction, E sub x, E sub y, E sub z, depends upon voltage changes. If there is no electric field, and that's the vector, E with an arrow equals 0, it means the vector is 0, all the components are 0. Therefore, you always have a delta x, delta y, delta z. That just means you can measure, the size of the object. Therefore, if Ex, Y, Z are zero at equilibrium, means that delta V must be zero in a conductor at equilibrium. I'm not saying there's no voltage. There can be a very high voltage. It could be thousands of volts. But the delta V, zero. In other words, at equilibrium, every part of a conductor is at the same voltage. And how does a conductor reach equilibrium? Well, talked in a previous video, because charge can move. So if you put an electric field on a conductor, charge will move. If it reaches equilibrium, electric field must be zero. That's the introduction to electric potential or voltage, how it relates to the field. We're going to come back to this in future videos, develop the topic further. Thank you for watching all the way to the end.